Yes. Hey, welcome back again. And yeah, now let's go over this really wacky problem. It's called burning tree. And yeah, when I was solving this, I had a smile on my face because the problem is so wacky. It's so cool also. So what will happen is that you'll be given a random node in a binary tree, and by some mistake it will catch it will catch fire, and you have to tell how much time it takes for the entire tree to burn down. Yeah, I told right, it's like pretty wacky. And yeah, find the minimum time to burn the complete binary if the given target is on fire. And yeah, it's given that every node takes 1 second to burn and the fire is spread to all the connected nodes. So for example, if the target node, yeah, it's 8 over here. So what will happen is after 8 will get 8 will be set on fire. After 1 second, 5 and 7 will catch on fire because 5 is actually connected to 8 and 7 is actually connected to 5. Yeah, that goes insane. Like yeah, after 1 second, 5 will catch fire, and after 2 seconds 5 and 2 7 and 2 will catch fire because 5 is actually connected to 2 and 7. And after 3 seconds, now let's just go directly to the target itself. So 10 is the furthest node. So what we'll do after 2 4 and 1, and then 3 6 9 10. Yeah, so totally it took 7 seconds. And yeah, on directly looking at this problem, it looks like impossible to solve, but it is actually a pure BFS problem, BFS again. Yeah, let's look at the tag. Yeah, it's again BFS only. It's not DFS. So what you can do is you can actually convert the given tree into a undirected graph. And when you have an undirected graph, you can directly do BFS from the given target node, and that will actually give you the amount of time it required for the entire tree to burn down. Yeah, and as soon as you get to know that, it will become really easy to solve. Just convert the given tree to a graph, like undirected graph, not the directed graph, because again, if it is directed, then it will obviously become a tree. So we have to convert it to an undirected graph, and all trees are graphs, but all graphs are not trees. Be careful of that. So yeah, convert the given tree to an undirected graph and start BFS from the given node, like target node, and you'll quickly reach your solution. Yeah, that's like super simple to do. Just the wording and the problem, looking at the problem makes it scary, but it's not at all scary. So yeah, again, to do BFS, there's only one thing which you need, and it's not a trusty wand or lots of money. It's just DQ. So yeah, if you have a just have a DQ, and now what you have to do, like, you have to have, you also need a default dictionary. Yeah, you need a default dictionary to convert the given tree to undirected graph. And I hope you know how to convert any given thing to an undirected graph. I think I have done it long ago. I think it was in Bellman Ford, I think. Yeah, both in Bellman Ford and Dijkstra, I have uploaded videos of that. And if you have watched that, then you will get to know how to convert anything to an undirected graph. So what we'll do. But yeah, this is a bit different because in that what happened was that we were given two arrays itself, like start node and end node, like start index and end index, two different arrays, and we constructed a graph from that. But in this, what we'll do is that we'll go from each node, and in each node we'll check if the node has left, and if the node has left, then we'll do a two-way mapping from node to the child and child to the node. And that's all. Like it's super simple to convert the given tree to an undirected graph. So yeah, again, you can do this using any kind of traversal you want, but I prefer BFS, and this is mainly in BFS, so let's do that. And doing it using other techniques will become difficult, I think. Yeah, this part you should again be able to write it with your eyes closed. Yeah. Now what you have to do again, if you remember, just take the current node. So let's declare our graph also. Yeah, you can do it using direct dictionaries also, but again, you have to check if the current node is present. Only then, if it is present, then append it. But using default dictionaries, our life will become easy. There's no need to explicitly check if the current node is present or not. Is it recording? Yeah, recording. Default dictionary type, yeah, type list. And if the no dot left exists, then let's do the two-way mapping. So Yeah. Now what you did is that you took the current node, like the root node or any node which you're on, and you did a mapping from its that to its left child. So from 1 to 2, you made the mapping. So now what you have to do is you have to also do the reverse mapping. So in other words, from 2 to 1. So let's do that, and yeah, just take the same line. Just do this node dot left dot data will be mapped to the node dot data. Now what happened is that you made the mapping from 2 to 1. Yeah, it's pretty simple. I told, right, and no slash over here. And do the same for right also. When node dot if node dot right exists, then node dot data will be mapped to node dot right dot data. So from 1 to 3, you did the mapping. From node dot right dot data, you map to the node dot data. In other words, from 3 to 1, you made the mapping. Yeah. Now let's just look at our graph once. Is our graph getting formed properly? Just be sure to debug everything, like print and debug whatever you're doing. Yeah, one is actually mapped to 2 and 3. One is mapped to 2 and 3. Two is mapped to 1, 4, and 5. Two is mapped to 1, 4, and 5. Yeah, that means that our mappings are happening perfectly. Now, like the crux of your like the core is done, the crux is done. Now only the BFS part is left, and again implementing BFS is pretty simple. So again, take the target node. So let's have a distance is actually 0 from the beginning. So take the target node and put it inside the queue. So target node is called as target itself, and put the current distance traveled, which is actually 0. And again, while queue exists, there's no need to do for I and length of queue, because we have to actually get the values from the graph itself. So node and the distance is actually you're popping the leftmost value. And yeah, so what will be the end condition? So whatever will happen when you are doing BFS on it will what will happen is that the final node will be reached last. So what we'll do, we'll continuously update our instances to the current distance. And what will happen is that when our queue is, when our entire queue gets depleted, we will actually have the furthest distance. So yeah, the actual answer to this is actually the node which is furthest from the current node. So if you consider 8, 10 is actually the furthest node to the current 8. I mean, when you consider 8, 10 is actually the furthest node. Like when you calculate the distance, so 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, as you see. So the actual answer will be always the furthest node from the target node. Again, I repeat it. So what you do, continuously update your distances. It's actually equal to distance. Yeah. So DISC. Yeah. And now what you do? Now again this should be like eyes closed. So for yeah, and again you obviously don't want to be like 5 to 8, 8 to 5, 5 to 8, 8 to 5. So if the node is actually in, let's again have a visited. Yeah, if the node is actually in visited, then obviously continue, because you don't want to revisit the same node again and again, or else you update the distance. And if you do this in reverse order, I think the answer might come out to be wrong. So let's not do that. So for the neighbor in graph at the position node, yeah, I hope what is happening over here. So we are taking the current node and finding all its neighbors, which is actually present in the form of an array. Where is it? Let's do another compile and run. Yeah, let's just comment this part out and let's print. And as you see, we are actually at this is the current node 8. So yeah, and for all the neighbors of 8, we are checking the values. And yeah, I think it's better if you, since 8 is a corner node, like it will be difficult to imagine. So let's take 5. Yeah, let's take 5. So 5 has 3 connected nodes. So for each neighbor of 5, So 5 has 7, 8, and 2. So for each neighbor in the current node which you are traversing, if the node actually exists in visited, then do not visit. So if the node is not in visited, no, it is not in visited, not in node. That makes no sense actually. Grammatically also it makes no sense. Yeah, if the neighbor is not actually in visited, then what you have to do? Just take the current node and append it to the what you tell queue itself. Yeah, to take to the queue. Yeah, the current node, don't append the current node, you will be left patching very went wrong, and logical errors are like really hard to catch. Yeah. Append the neighbor and the count. It is actually called dystoria. But increase the distance by one because on each traversal you are actually implementing the distance. So now you can directly return the distance. So now what will happen is that on each traversal the distance will actually be updated. And on final traversal you will like the distance will be updated with the furthest node. Yeah, you know why? Because we are actually checking for the current node not being in visited, but we are not actually adding the current node to the visited itself. Yeah, don't forget to add the current node which you are checking to the visited. And yeah, let's just submit it. And yeah, this always feels good to watch. And don't watch this because once for trying on myself and then one for submitting. And yeah, again it was yeah again as soon as you convert the given graph to given tree to a bidirectional or undirected graph, so it will become very easy to solve. Just start a DFS from the given target node, and and you will actually get the answer. Like don't try to start a BFS. Yeah, you can actually do a BFS also. Like there's no difference in doing BFS and DFS because yeah, it will directly go directly to tell itself in the beginning. Yeah, it depends on which approach you want to use. But I have used BFS, and if you are feeling explorative, then try out the DFS solution and notify me in comments or something. And yeah, that's all for it. Thank you for watching. Solve more DSA, solve more problems like this, which look wacky at first, but actually have pretty simple solutions. Yeah, that's all for it. Thank you.